Hi there, welcome to a new physics lesson filled with adventure and discovery. Today, our topic is the second law of thermodynamics. And so we already talked about the first law of thermodynamics, and we're moving on to the second law, this second law is kind of a downer, but it's a very important piece of how our universe works. The second law of thermodynamics is also called the law of entropy. So what is entropy? Well, entropy is a measurement of randomness or disorder of a system. Or, in simpler terms, it's kind of this idea of disorder. That things left to themselves, if you just leave it by itself, it's going to become more disorderly or broken down. And so the more disorder something has, the more entropy it has, and vice versa. And all processes lead to more disorder. So for example, let's say I went to the beach and I built myself a sandcastle. Okay, if I were just to leave that sandcastle, after a while, it would become more and more disorderly because of the waves, because of the wind, because of little kids stomping around. Okay, it's going to become more disorderly. That sandcastle is going to gain in entropy until it's kind of back to how it originally was. And so that's kind of an important property of our universe. That everywhere in our universe, things tend to become more disorderly, and that's why our hot objects tend to become cold after a while. Houses break down. Our bodies will eventually decay and die. Law of entropy at its work. And so, so the second law of thermodynamics states that the entropy of the universe will always increase over time. And so even though we can reverse entropy, we can make decreases in entropy by exerting work into certain processes. Overall, the things we do eventually increase the entropy of our universe and system. So here's an example of our refrigerator. When we cool things, when we freeze things, we're actually making it more orderly. We're decreasing the entropy. However, in order to do that, our refrigerator has to make air hotter. Okay, the air after we freeze that ice has greater kinetic energy and is more disorderly, and so we have a large increase in entropy in order to have this small decrease in entropy. It's a kind of interesting thing to think about. So if you think about cyclical processes, this also applies when we're talking about engines and we're talking about our mechanics. When we have a cyclical process, unfortunately, some of that heat is going to become more disorderly. Some of that energy is going to become more disorderly. And so because of this, we run into a few conclusions. First of all, according to the first law, the energy that we put into the engine should be equal to the work outputted by that engine. However, we don't experience that. And so because of that, we have the second law of thermodynamics, which because of that, we can never even come close to being equal to the amount of heat put into the system. So the first state, in all conclusion, the first law states that we can't get more than we put in, and then the second law states that we can't even become even with that. And so whenever we have an engine working to move our vehicles or to power a certain mechanical device, there's always a loss of this energy. There's some energy that's being transferred from our what we call a hot reservoir, or QH, to a cold reservoir, which is usually the air around the engine or the walls of the engine. There's some energy that's transferred and lost by our engine. And so we can figure out the efficiency of an engine by using this little equation, where the net work from our system divided by the heat reservoir will give us the efficiency. Or in other words, if we have our heat of our hot reservoir, or the heat lost to our engine, subtracted by the heat added to our engine, divided by the heat loss, we can figure out efficiency. Or another simpler way to put it, if we simplify it, we can have 1 minus the cold reservoir, the heat loss, divided by the heat added to our system. And so here's an example of that. We have a gasoline engine, and receives 204 joules of energy, but it loses 153 joules as exhaust, as unused fuel. And so if we plug that in, our cold reservoir, the heat loss is 153, the heat that we put in is 204, And so we come out to a percentage or a ratio of efficiency, which is our engine being about 25%, which is kind of sad. But that's kind of one of the applications of entropy. And so thank you so much for joining us, and we'll see you next time.